All right, please get out the relating f prime and f double prime additional worksheet that we went over last week. We're going to add something to the back of it. So my plan is to finish up the section today. We just have like one brief page to go over, so it's not going to be that difficult. And then we're going to take a look at kind of a graphing example, why we have all these different characteristics to analyze. And if we have any remaining period or time left in the period, you can use it as kind of some homework opportunity. Tomorrow we're going to have an activity day. We're going to be doing a puzzle or matching activity. And then Wednesday is a free response, which means Thursday is going to be a partner quiz. I'll let you know who you're working with later on this week. Friday is going to be our review day, and then next week, Monday, Tuesday, is going to be our unit test. And I think, Christian, was it you that asked, like, what's going to be on this one? Yeah. Okay, so it's just 4.3 and 4.4. There's no implicit, there's no related rates, because we already did that in the other test. Okay, so another 2-section test. All right. On the worksheet, can you flip it to the back? We're going to kind of write some additional relationships. If you look at the front page, I believe the top mentioned positive, negative, 0, right, in that table, okay? When we flip it to the back, I want to pay a little bit more attention to like increasing and decreasing. I want you to just have another chart to go through in your notes to help you reference like what characteristic it is you should be analyzing to determine what a different function is doing. For instance, how do you know when to look for above x-axis or below? Or how do you know when to look for increasing or decreasing? Because those are different characteristics entirely. So we're going to kind of create a list or a flow chart, if you will, on the back of that page. So I want us to assume that we're starting with a derivative graph. It could be a second derivative. I don't care what it is, but for here we're just going to assume it's the first derivative. And we're going to list when that derivative graph is positive, negative, or 0, what does that tell us either about f of x or the second derivative? Okay, either one. And then what if we were to analyze the increasing, decreasing, or max and min nature of the first derivative graph? What would that tell us about the original or the second derivative? Doesn't matter. Can we start listing some of these? Am I really? I was wondering why we weren't writing anything. I'm sorry. Okay, so first derivative. This makes more sense now because we were just looking up here like deer in headlights, and I didn't see any pencils moving. Okay, thank you, Cole, for speaking up. So. It's a Monday. I thought for sure he wasn't writing anything yet. It's a Monday. All right. What if the first derivative is positive? What can we conclude either about f of x, the original function, or the second derivative, if we have a connection there? Yeah? F of x is increasing. All right. Do we have a connection to the second derivative if the first derivative is positive? How is the second derivative related to the first derivative? It's the slope. So if the first derivative is positive, does that tell us anything about the slope of this graph? No, because if something's positive, it's just telling you a location. It's above the x-axis. So if the first derivative is positive, we actually don't have any connection to the second derivative, because the second derivative would be the slope of this graph, meaning is it increasing, decreasing, or at a max and a min. So if the first derivative is positive, negative, or 0, we're only going to have connections to the first derivative, or the original function rather, here. So when you analyze positive, negative, or zeros on a derivative graph, your conclusion is something about the original function, always and forever. What if the first derivative is negative? Original function decreasing. What if the first derivative is 0? F of x max, min, or level. Okay, critical point, right? A possible max or min, because you could be level.
I don't know if it's kind of off topic. That reminded me of a question on the homework.
Yeah.
It was like one of the tables that I set up, and it had positive, 0, positive. So
It should never be 0. Like when you're filling out a sign chart.
Oh, it was like, yeah, not wasn't sign. It was like a normal one. But it was like, oh wait, you mean sign like trig sign?
No, I mean, no, sign like positive, negative.
Oh, yeah, okay. That was the one. That was the one. And it went positive, our critical point, and then it was positive again. That shouldn't happen though.
If it's, so in your chart, it was positive.
Yes.
And then
Positive right there again.
But this was a critical point?
Yeah.
So this would be level.
So that's like,
So you're increasing, level, increasing.
Okay, yeah, I got it.
Okay, so this is your slope of 0, and then you're increasing before, increasing after.
Okay, I got you now.
Got it? We're just getting our laughs in today. What if the first derivative changes positive to negative? F of x. Good news. Max. All right. First derivative changes negative to positive. F of x min. Okay. So a first derivative graph, if you analyze above x-axis, below x-axis, on x-axis, you can only justify or conclude something about the original function. Now, what if, for instance, they gave you a second derivative graph? What if I threw in a prime mark here? What would all of these change to? F prime. Okay, if you add a prime mark, then you have to add a prime mark to your conclusions. So if it was a second derivative graph, positive, negative, 0 only tells you something about the first derivative information. Okay, we're not going to assume that though. We're just going to keep it as the first derivative. But notice how those relationships are still true. You can add a prime mark to each set. All right, let's take a look at, given the first derivative graph, if you analyze increasing, decreasing, or max and min. What if the first derivative is increasing? The slopes are getting steeper. What can we conclude about the original function or the second derivative? Yeah?
The second derivative is positive.
Second derivative, positive. If the first derivative is increasing, the slope is positive. Do we have a connection to the original function? If the first derivative is increasing, the original function is growing exponentially. Okay, so like that. Okay, so curvature, growing exponentially. Yeah. Concave up. Okay, you can also see if the second derivative is positive, the original function is concave up. We can do similar statements for decreasing. The second derivative is negative, which means the original function is concave down. What if the first derivative has a max? What does that tell us about the second derivative or the original function? Either one. Yeah?
The second derivative has 0 undefined.
0 undefined. Okay, so notice how if you have a max, that means you change increasing to decreasing. So the second derivative would have to change positive to negative. So second derivative is 0 or undefined, because maybe you have some type of jump where you can go from positive to negative. Do we have a similar relationship, though, to the original function? If the first derivative has a max, the original function would be changing concave up to concave down. If you change concavity, point of inflection. So, inflection point. Good. And last but not least, minimums. If the first derivative has a min, the second derivative is changing negative to positive. So that means you must cross 0 or you're undefined. Like maybe you have that jump. If we check out original function, that would change concave down to concave up. So that would be another inflection point. All right. So hypothetically, let's say that they gave us the second derivative graph. If I throw in a prime mark up here at the top, I'd have to throw in a prime mark into all of these conclusions. So the third derivative would be positive, or the first derivative would be concave up. Okay, so you can keep adding prime marks to get all those conclusions. Now, we're not going to deal with the third derivative, so odds are you're not going to do that. But notice how if they do give you a second derivative graph, they could ask you about the concavity of the derivative. Okay, because it's a second derivative and a first derivative relationship there. Okay, does that help? Another list? Okay, more relationships. Good. All right, let's take a look at 257. We're going to take a look at some kind of previous AP questions. These are more multiple choice based, non-calculator though. The ones that we did on Friday, you were able to use a calculator. All right, the derivative of a function g is continuous, no holes, no jumps, no asymptotes in the derivative graph, and has exactly 2 zeros. Selected values for the derivative are given in the table. If the domain of g is all real numbers, then g is decreasing on which of the following intervals? So they're giving us derivative information in a table, and they're asking us about an original function g. So we got to think about that connection, that relationship. If we want the original to be decreasing, what characteristics should we be looking for the derivative? Negative. All right, so g prime is negative. Where does that happen on the table? What do you think?
-1 to 1.
All right, so we're definitely negative in here. What if I wanted negative 1.5 or 1.5? Would we still be negative in there? We're continuous, so no holes, no jumps, no asymptotes. and you only have 2 zeros. It would be negative 2 to 2. Yep. If you look at the table, this negative 2 would be a maximum on g because you change positive to negative on the derivative, and then positive 2 would be a minimum. So you should be decreasing in between maxes and mins. So we'll actually use negative 2 and 2 as our starting points. Looks good. All right, the second derivative of a function is given by this equation. The graph of the second derivative is shown. For what values of x is the first derivative have a max? So they give us second derivative information. They're asking us about first derivative max. Can we list what we should be looking for? Zeros, okay. And if we want a maximum, we want the second derivative to change. Good. Positive to negative. So here's the graph of the second derivative. Where do we change positive to negative? A? Yep. Did we even have to use the equation? No. Okay. Sometimes they'll do that. They'll give you more information than what you actually need. Not to say that you couldn't use it. I'm just saying you can approach it by looking at the graph. Okay. Are we doing okay so far? Okay. If h is twice differentiable, so you can take 2 derivatives with no problems, like no sharp points, no vertical tangents, no endpoints, such that h of x is always negative, for what values does the graph of g have a max if the derivative equation is that? Oh man. If we want g to have a max, what do we need g prime to do? It's a 0, and if it's a maximum, changes positive to negative. Okay? Now they don't give us a graph to actually analyze to help us with that. So how can we take an equation for the derivative and see if it changes positive to negative? Basically, that's what a sign chart does. Sign meaning positive or negative. Okay? So,
You can plug in the x values and it gives
Yeah.
you answer options.
or you can test, we're going to test those. Okay? Can we, if this is the first derivative, can we find the critical points where the first derivative is 0? 3, negative 3. Is h of x giving us a 0? Never, because it's always negative. All right, so let's do negative infinity to negative 3, negative 3 to 3, 3 to infinity. All right, pick something between negative infinity and negative 3. Negative 4. 9 minus negative 4 squared. Something negative, okay, times h of negative 4, which is always negative, so that would be positive, okay? Something between negative 3 and positive 3, 0. 9 minus 0, positive, times h of 0. That's always negative, so positive times negative is a negative. Something between 3 and infinity, 4. 9 minus 4 squared. Negative times h of x, which is always negative, positive. So we got to change positive to negative. Looks like that happens at negative 3. Now, I want you to pay attention, okay? I see this happen all the time. People, students, will look at this question and automatically pick A because those are the critical points, right? It was asking you for a max. So critical points are possible maxes or mins. You have to test them to see if they actually are. So this one would be D. All right, last one. A table of a function of a twice differentiable function is pictured to the right. Which of the following statements are true if f has only one x-intercept between -3 and +3? All right, the first derivative is negative, okay, less than 0, on the interval -3 to +3. They're asking us about the first derivative, and they gave us original function information. Is that statement true or false? What should we be looking for? Is f of x decreasing? Yes. All right. F of x has an x-intercept between 1 and 3.
Yes.
Why? It changes sign, okay? That's our intermediate value theorem from earlier this year. If you know a y value, in this case 0, is between 2 and -3, you know there's an x-intercept between the x values of 1 and 3, definitely. All right, the second derivative is positive on the interval from -3 to +3. So they're asking us about the second derivative, but they give us original function information. What do we need to look for? Concavity, but we don't have a graph to analyze concavity. So you could. I mean, if you tried to draw it accurately, you could. Can we turn this original function information into derivative information? That's slope, right? Can we find the slope between these points? Yeah? So if we go 2 units on the y and 2 units on the x, our slope would be, if your rise is 2, if your rise is -2 and your run is +2, 8 minus 10 over -1 minus -3, -1. Okay. If your rise is -6, but your run is +2, -3. If your rise is -15 and your run is 2, -7.5. Okay? So if we want the second derivative to be positive, we want the first derivative to then be increasing. Are these numbers increasing? No, they're decreasing, right? Because -3 is less than -1. So we'll say this one is false because first derivative is actually decreasing. So I suggest looking at the numbers more than graphing it, because depending on how accurate your graph is, you might not see the concavity like you need to. Okay? So which ones are true? We'd have 1 and 2. All right. We doing okay? Those are previous AP questions related to some of the topics that we've been doing. All right. Do me a favor, and on the back of that page, we're going to go ahead and take a look at this example. We're going to graph this without a calculator, by hand, using some calculus. And then we'll go ahead and check it on our calculator just to make sure it makes sense. So we're going to find increasing intervals, decreasing intervals, if we have any maxes or mins, where we're concave up, where we're concave down, maybe if we have any inflection points, and I think y-intercepts are very easy to to figure out just by looking at an equation. Okay, so, oh, we'll do domain as well. If we can figure out all these different characteristics, we should have no problem graphing this by hand because we have all these different properties to it. Can we list the domain of that function? Is there any x value that you would think would cause an issue? 0 to the power 0 times 12, 0 minus 0, 0. You actually found the y-intercept. If you plug in 0 for your x's, that's going to tell you where you are on the y-axis. So we know we actually go through the origin. Notice how this equation's not a fraction, so we really don't have to worry about if we're undefined anywhere. So domain's all real numbers. To figure out increasing, decreasing, max, and min, we can use a first derivative sign chart to help us with those. And then concavity, we could do a second derivative sign chart. Maybe go another round. Let's do it. Can we find our first derivative?
Probably.
Yep. 12 times 2/3.
Probably something like 8.
8. There you go. X, or 8x to the negative 1/3. And then we'll have minus 4. While we're at it, let's find the second derivative. Can we go another round? Negative 8/3 x to the negative 4/3. All right, so in order to use a sign chart, we're going to have to find the critical points for our first derivative. Let's set it equal to 0. I'm going to rewrite this since we have a negative power. I'm going to make it x to the 1/3 on the bottom. All right, so critical point, where the first derivative is 0 or undefined. Is our first derivative undefined anywhere? Is there a number that you'd plug in here that would cause an issue? 0, because we have a fraction now, right? So x equals 0 is a critical point. It makes your first derivative undefined. Let's see if we can find an x value that would make this equal 0. So maybe we'll add the 4 over. You can multiply the x to the 1/3 over to get rid of the fraction. Divide by 4. How can we get rid of a power of a third? AKA a cubed root. Cube both sides. So we get 8. Alright, so there's another critical point. Let's do the same thing for the second derivative. Okay, before we do a sign chart, maybe we'll just keep this process going. Maybe we'll clean up the second derivative a little bit more. Move it to the bottom. Is a spot where this second derivative might be undefined. 0 again. Okay, so this would be a possible inflection point for the original function. Now we also have to solve for if the second derivative is 0 at any spot. If you multiply the denominator over, does 0 equal 8? Nah, not really. Okay. If you add another, I just got that. If you add another 0. All right, so we do have a possible inflection point, but notice how it came from the undefined part, not the actual 0 part. So using these critical points and possible inflection points, we're going to take the domain of all real numbers, negative infinity, positive infinity, and we're going to create our sign charts. So negative infinity to 0, 0 to 8, 8 to infinity. And then for the first or second derivative, we'll do negative infinity to 0, 0 to infinity. All right. Pick a number between negative infinity and 0. Negative 1. Okay, we're going to plug it into our first derivative. The cubed root of negative 1. 8 divided by negative 1. Minus 4. Negative. Okay. Something between 0 and 8. 1. The cubed root of 1. 8 divided by 1. Minus 4. Positive. All right. Something between 8 and infinity. 10. Cubed root of 10. Cubed root of 10 is something bigger than 2.
Yeah.
8 divided by something bigger than 2. Something smaller than 4 minus 4. Negative.
Thanks, Caden.
All right, let's do the same thing for the second derivative. Something between negative infinity and 0.
Negative 1. I don't know if that's
Okay, the cubed root, let's check this out. Cubed root, because the denominators are 3, cubed root of negative 1 is negative 1. Raise it to the 4th. Negative 1 to the 4th. 1 times 3, 8 divided by 3. Positive. All right. Something between 0 and infinity. 1. 1 to any power. Times 3, 3, 8 divided by 3, still positive. Okay? So it looks like, if we do our little justifications here, f of x is decreasing on the first interval, and then has a min. Then increasing, and then has a max, and then ends by decreasing. From the second derivative sign chart, we are concave up. And then at 0, we have no curvature. And then concave up on the last interval. Oh, wait, these should be negative. I missed this. We see that? Negative. So these should be negative, negative. Concave down, concave down. So notice how if we don't have a sign change, we have no inflection points, okay, on f of x. Zoom out. All right, let's try to find the coordinates of the max and the min. So if we were to plug in 0 into the original function, do we know what we'd get out? Yeah. 0, we already did that. That happens to be your y-intercept. If you were to plug in 8, let's see if we can find the max. So the cubed root of 8 would be 2. 2 squared is 4. 12 times 4, 48. Okay, so 48 minus, if we plug in 8 here, 4 times 8, right? 48 minus 32? 16. All right, let's graph it. All right, domain, all real numbers, so no holes, no jumps, no asymptotes. Y-intercept at the origin, and this happens to be a min. We have a maximum at 8, 16. So I'm just going to roughly put that here. Okay, we know that's a max. Let's analyze this a little bit further. Notice how this critical point of 0 came from the undefined nature of the derivative. If a derivative is undefined, what's possibly happening at this spot? We know it's a minimum from the sign chart, but if a derivative is undefined, there's no holes, no jumps, no asymptotes. It could be a vertical slope. It could be vertical slope, sharp point, or
endpoint.
but it's not an endpoint, right? Because it's in the middle of the graph.
You're right.
Okay? So if it's a critical, if it's if it's either a vertical slope or a sharp point, and you know it's a minimum, of the two options, what would this one be? Sharp point. So this has to be something sharp here. And if it's a minimum, you know it goes above like that. Okay? So let's see. From negative infinity to 0, we should be decreasing, but also concave down. So something like that. Decreasing, concave down. After 0, which was a minimum, we should be increasing, but also concave down. So we're going to play connect the dots, concave down section, bless you. And then after 8, we should be decreasing and still concave down. Kind of. Let's see if we can get it. 12x to the 2/3 power minus 4x. Window, I'll do negative 20, positive 20. Notice how our max was at 16, so we want to make sure we can see it. All right, so we have that left-hand side. You might want to go a little higher if you want to see more of it, but we definitely have the left-hand side coming down. Sharp point at the origin. Notice how it bounces very drastically there. And then we have our maximum at the top, like we said. So we had a very rough sketch, but we did it by hand using some calculus. Increasing, decreasing, concavity, maxes and mins, points of inflection. Pretty good, guys. All right. We'll stop there. Tomorrow we're going to have our activity day, kind of matching some graphs, and then we'll go ahead with our review and quiz later this week.